In this part, we aim to address the uniqueness question by suggesting something stronger than the mutual coherence, the Babel-Function. We start by the statement that while simple to use, the mutual coherence is in fact very crude. Why is it so? Consider the case where A has two identical atoms. In this case, mu becomes 1 and all our analysis collapses. Furthermore, if two columns are close by, this implies that mu is very close to 1, and again, our results become too weak. Indeed, we have seen that there is a large gap between the 1 plus 1 over mu and the spark bounds for uniqueness. One is of the order of square root of n, at best, and the other could be as high as n plus 1. An interesting question to ask is this: does the mutual coherence has a true practical meaning, or is it only a theoretically convenient tool with a pessimistic prediction? While we will not answer this tough question here in full, we turn now to propose the Babel-Function, which fixes some of the difficulties that the coherence has. The definition of the Babel-Function mu1 of k is given here, and the first thing to notice is that it looks quite complicated. So let's make sense of this formula. We get the matrix A and choose an arbitrary set of k columns from it, denoted as capital lambda. We choose another column aj from outside of this set, and then compute the sum of the absolute inner product of all the vectors in lambda with aj. Now imagine that we repeat all this process for all the possibilities of choosing lambda and aj. And let's maximize the above mentioned sum. This is mu1 of k, the Babel-Function. The above description must leave you with the impression that computing the Babel-Function is a combinatorial task of exponential complexity. Actually, this is very far from the truth. And in fact, computing mu1 of k is rather easy. We start by computing the Gram matrix G. Then we take the absolute values of the entries of G and sort each row in descending order. The maximal element in each row is obviously 1, taken from the main diagonal, and it will be leading each row after the sorting. The rest of the row contains values in the range 0 to mu. We remove the first column from the resulting matrix, as these ones contribute nothing to the computation of the Babel-Function. We are nearly done. Now replace each row with an accumulated sum of it from the left to the right. That is, the first entry remains unchanged, the second becomes the sum of the first two, etc. As a last step, go to the kth column and search for the maximal value. The row it is found in defines the index j in the computation of mu1 of k. And the first k elements are in fact the set lambda. The maximal value itself is mu1 of k. Why should we turn from the mutual coherence to the Babel-Function? Well, because the mutual coherence characterizes pairs of columns from A, whereas the Babel-Function naturally extends this to larger sets. How are the two related? First, observe that by bounding each of the inner products by the regular coherence mu, we see that mu1 of k is upper bounded by k times mu. Secondly, mu1 of 1 is trivially mu, the regular coherence, by definition. Indeed, this implies that the Babel-Function does not provide a remedy to the case where two columns are identical. Another property of mu1 is the fact that it is monotonically increasing as k grows, and the steps are getting smaller and smaller. This exposes the source of strength of the Babel-Function over the regular mutual coherence. If the growth is slower than mu in each step of the increasing k, the Babel-Function is more faithfully describing the situation for us. We will not provide a complete analysis of the Babel-Function, but the following observations are easy to verify. First, as long as mu1 of k is smaller than 1, this implies that any set of k plus 1 columns is linearly independent. This in turn says that the spark is bigger than k plus 1. Here is a graph illustrating this property. Observe first the line mu times k and the curve describing mu1 of k, which grows slower than the line. The spark is predicted as the first k that causes mu1 of k minus 1 to cross the value 1. Due to the slower growth, this prediction is better than using the regular mutual coherence. Can we use the Babel-Function to get an alternative uniqueness result? The answer is positive. Here is the original theorem that we have already seen, which bases its claim of the uniqueness on the regular coherence. Armed with a bubble function, a new condition for uniqueness can be posed. If the given solution is sparse enough, having k non-zeros, and if mu1 of k plus mu1 of k minus 1 is smaller than 1, then this solution is necessarily optimal.